All right, hello, calculus people. We're going to look at motion in space now, which we're going to kind of formalize some ideas which are already, we've talked about and kind of implied a few times, but we're going to look at, I guess a little bit more formal definition of some of these concepts. So if we have if we have r of t is the position vector of some object moving through space. The first derivative, r prime, we can call v of t. This is the velocity. The absolute value of the velocity, I'll write it in two ways. The absolute value of r prime or the absolute value of the velocity. Absolute value. It's the magnitude of the vector. I don't know why I'm calling it absolute value. This is the speed. So speed can't be negative. So the magnitude of velocity is speed. Speed also doesn't have a direction. It's just a magnitude. And then finally, the acceleration. If we take the second derivative, which is the same as the first derivative of the velocity, we call that acceleration. Okay, so let's take an example. Let's suppose some object is moving around with a position vector t cubed I plus t squared j. So the first derivative, the velocity, is going to be just 3t squared I plus 2tj. The second derivative is going to be 6ti plus 2j. So if we wanted to say if when t equals 1, the velocity at time 1 is going to be 3i plus 2j. The speed at time I, the speed at time 1 is going to be the square root of 3 squared plus 2 squared. So that's going to be 9 plus 4. That's the square root of 13. That's units per time unit. And then the acceleration at time 1 is going to be 6i plus 2j. So the acceleration, that's like the direction in which this thing is, the direction in which the acceleration force is going. Direction and magnitude of acceleration. I don't know if force is the right word, but yeah, that's the direction and magnitude of the acceleration. All right, let's take another example. Let's say the position vector of this object is t squared, e to the t, and then t e to the t. So the velocity vector is going to be just 2t e to the t. That's the derivative of e to the t. And then using the product rule, it would be e to the t plus t e to the t for the derivative of that third component. The absolute value, the speed of this thing, I keep saying absolute value. It's not absolute value. It's a magnitude, right? This is going to be a little bit less clean and pretty, but I'm still going to do it. So we have 2t squared plus e to the t squared plus e to the t plus t e to the t squared. This is going to be 4t squared plus e to the 2t actually ends up being a factor of, well, you know what, let's do this out. E to the 2t plus, we have e to the t, you know what I'm going to do? I'm going to clean this up here. Just going to note that I can factor out e to the 2t, and it's going to be 1 plus t squared. So in fact, I'm going to 1 plus t squared, that's e to the 2t times 1 plus 2t plus t squared. Okay, and we already have an e to the 2t, so actually there's going to be 2e to the 2t plus e to the 2t e to the 2t plus t squared e to the 2t. Now this is, again, it's not pretty. It doesn't really matter what I do to it. It's not going to make it pretty. But that is the speed at any given time. The acceleration is going to be found by taking the derivative of velocity, right? So it's going to be 2, then e to the t, and then we have e to the t plus e to the t, plus t e to the t. This is to say this is the derivative. This here is the derivative of t e to the t, which I already did, which actually, I can clean this up just a teeny bit. That would be 2e to the t plus t e to the t, which if I wanted to, I can write that I can write it as e to the t times 2 plus 1, but I don't want to do that. Okay, finding velocity, finding acceleration is just a matter of taking derivatives. Now suppose we have some starting conditions. We know that a particle is starting out at the coordinates 1, 0, 0, so that's its position vector at time 0 is 1, 0, 0. We have an initial velocity of 1, negative 1, 1, so that's v of 0. And if we're given the acceleration function at time t, we can actually kind of backtrack using integration to find the position vector function. So v of t is going to be, I'm going to integrate the three terms, so it's going to be 2t squared plus, I'll call it c1, comma, then I'm going to have 3t squared plus c2, comma, and then I'll have t plus c3. Now, to find out what those c's are, I just plug in 0. V of 0 is going to be 0 plus, well, I'll just write it c1, comma, c2, comma, c3. And because I was given this, starting conditions, that actually gives me those three constants. So in fact, v of t is 2t squared plus 1, 3t squared minus 1, and then t plus 1. Now I can integrate a second time to get the position vector, again with constants. So I'm going to have it's going to be 2/3 t to the third plus t plus, I've already used my c's. I'll just call these d's, d1. And then I'm going to have t to the third minus t plus d2, and then I'll have 1/2 t squared plus t plus d3. And if I plug in 0 for t, I just get d1, d2, d3. And I was given my initial condition of 1, 0, 0. So in fact, that's going to be my values. d1 is 1 and the others are 0. So the position function for this thing is in fact 2/3 t cubed plus t plus 1. And then for the second component, we have t cubed minus t. For the third component, it's 1/2 t squared plus t. And that's how you can backtrack. It's just a matter of doing integration and using the starting conditions to find out what those constants are. So a little application of this. Newton's second law of motion says the force is mass times acceleration. Mass being a scalar, but acceleration being a vector, we'll have a force vector resulting from this law. So for example, okay, suppose an object has mass m and it's moving in a circular path with constant angular speed omega. This is an omega, it's not a little w. The curve, it's extra curvy, so that's an omega, lowercase omega. So this is the position function. R of t is a cosine omega t I plus a sine omega t j. And so I want to find the force vector. And so the force vector, right, I'm going to have to find the first derivative, and that's going to be a times the sine of omega t I times an omega minus a times cosine omega t times the j vector times an omega. The second derivative is going to be, well, I know I'm going to get another omega out, so I might as well. Oh, why did I do this? I put the negatives in the wrong places, sorry. The first term is minus, and the second one is plus. The derivative of sine is cosine. Derivative of cosine is negative sine. But let's finish this. I'm going to get, this first one is going to be a, then omega squared, cosine omega t I, minus now a omega squared times the sine now of omega t j. This is the acceleration, and so the force vector, force at time t, is going to be the mass times the second derivative, right? And so this is going to be the mass times a times omega squared times this vector, negative cosine omega t, comma, negative sine omega t. So if we were to graph this thing, as this thing is moving around, this is the radius of this path, right? It's kind of going around in this circle in this direction. If let's say, for example, if omega t is equal to 30 degrees, suppose, so this thing is at this point, the acceleration is going to be in the direction of the negative cosine of 30 degrees, which means that like this is going to be the direction of the acceleration. It's going to be the opposite vector of the location where this is found, right? At any given time, the force at time t is actually negative mass times acceleration times a, sorry. Actually, let's put it like this way. Mass times omega squared times r of t. So wherever this object is, the acceleration is always going to be pointing straight towards the origin. You can see what I just did there. I took out the minus sign, but actually, if I shove that a back in to the two components, then I'm back to the position function. Okay, suppose a projectile is fired with an initial speed of 150 meters per second at an angle of elevation of 45 degrees from 10 meters above the ground. So I'm going to draw a little, that's 10 meters above, 45 degrees. This is kind of the path that it takes. Okay. We want to know, where does it hit? How far away from the starting point and at what speed. And we want to remember that the force of gravity is negative 9.8 meters per second squared. That's gravity, and that's actually going to be our kind of starting point. We're going to put all of these things in terms of vectors. So the acceleration vector at any given time is going to be 0 horizontally and negative 9.8 vertically. So we only have two directions in this. We only have a two-dimensional kind of example here. The velocity at time t is going to be some constant 1 for the first component minus 9.8 t plus some second constant. Now the thing is, my initial velocity I can actually get as the initial velocity is actually going to be the speed times cosine of 45 degrees, comma, the sine of 45 degrees. So we can actually write this. This is actually going to be 150 over root 2, comma, 150 over root 2. These are actually both the constants, and so you can actually write this 150 over root 2, comma, negative 9.8 t plus 150 over root 2. Now to find the position function, we're going to integrate this, and so we're going to get 150 over root 2 t plus the starting position, right? What is the starting position here? We're going to call that 0, comma 10. So it's actually going to be 0 horizontally. And then we have negative, it's actually going to be half of this now because it's going to be t squared. So that's going to be 4.9 t squared plus 150 t over root 2 plus the starting height, which is at 10. And now we can solve, and we want to find when is negative 4.9 t squared plus 150 t over root 2 plus 10 equal to 0. You can solve a quadratic and get that. So you can solve this and you find one of the two solutions to this quadratic is 21.74 seconds. And that's the only, I mean, the other solution is negative, and that's backwards in time. That doesn't make any sense. And so the velocity at time 21.74, I'm going to just evaluate that. So the velocity vector at time 21.74 seconds, if you work that out, you get 106.07 and negative 106.99. And so the speed at 21.74 seconds is that's the magnitude. That's the square root of 106.07 squared plus 106.99 squared. The negative doesn't matter here. So that speed when it hits the ground, 150.65 meters per second. Okay. And this is, of course, assuming there's no wind and that the ground is flat and all that stuff. So let's take a look at this one. With what speed must an arrow be fired if the angle of elevation is 10 degrees and the height that it's fired from is 12 meters? Now it's trying to hit a target 40 meters away at a height of 3 meters. So what we have is this. So the starting point is the position, let's say 0, 12, and the angle of elevation is going to be just 10 degrees. And so we want to hit that target. Okay. So again, we can say a few things. Let's put the starting position. The r at time 0 is 0, 12. The starting velocity is, I'm going to put it as some unknown speed times the vector cosine 10 sine 10. I don't know what speed we need, but I know that it's going to be looking like that. And the acceleration, so we have 0 and negative 9.8. We're going to work backwards now, take the velocity at time t, and this is going to be s times the cosine of 10. In fact, let's write it like that, and then comma, negative 9.8 t plus s times the sine of 10. The position vector then, r at time t, if I integrate that a second time, it's going to be s times the cosine of 10 times t plus 0, that starting position. Then we have negative 4.9 t squared plus s times the sine of 10t plus the 12. And so my goal is I want this thing to, well, let's see, when is this going to reach 40 units across? When is 40 equal to s cosine 10 of t? Well, t is going to be 40 over s cosine of 10, whatever that is. Well, okay. So what I want then is to solve this thing by plugging in 40 over s cosine 10 in for t. And I want at that time, I want so like at r at time 40 over s cosine of 10, I need that to be 40 comma 3. So I know that the x coordinate's going to be fine, the x component, but for the y, I'm actually solving this equation. Let's set 3 equal to negative 4.9 times 40 over s cosine 10 squared plus s times the sine of 10 times 40 over s cosine 10 plus 12. And I guess I could, if I wanted to, I could like cancel these s's at least. But everything else is just a matter of, well, let's see. Well, you can solve this yourself, but this is what you get. So solving this thing, you get the speed that you need is 22.44 meters per second. So if we use the notation just v, lowercase v, is the speed, that's the magnitude of the velocity vector, we can actually write that the unit tangent vector at time t is just the velocity divided by the speed. And so we can actually write v times t equals the velocity. Like we just multiply both sides of that equation by little v. So if you take the derivative and use the product rule, right? The acceleration, which is the velocity, the derivative of velocity, is going to be v. No, speed is still a function of time, so it's a function. So it would be v prime times t plus v times t prime. And if you recall the curvature is the magnitude of the magnitude of the unit tangent, the derivative of the tangent vector over the magnitude of the derivative of r, right? Which we can write as the magnitude of t prime over the speed. So we can actually write kappa times v is equal to the magnitude of t prime. And if you remember that the normal vector is just the first derivative of tangent divided by the magnitude of the first derivative, right? Plugging in this kappa v, the curvature times the speed, we can get a different. We can write magnitude of that unit vector prime is kappa times v times the unit times the normal vector. And so putting that back in, putting that in over here, we can write the acceleration is the velocity, or sorry, it's the speed, the first derivative of speed times the tangent vector plus the speed, well, squared times kappa times the normal vector. The reason that this is useful is what we get is for any like as this particle is moving along, remember we have the tangent vector and we have the normal vector. What we get is a tangential component and a normal component of the acceleration. Actually, the tangential component is the first derivative of speed. The normal component is the speed squared times the curvature. This is what we call the tangential component of acceleration is what we call is speed prime, the first derivative of speed, and the normal component is the speed squared times kappa, or the speed squared times the curvature. This is just a way of breaking up the acceleration velocity, acceleration vector, into these two components, and this is very useful for deriving kind of laws of planetary motion, but I'm not going to go into all of that. So I'm going to stop here. That's going to wrap up this chapter on vector functions, but we'll continue doing some more stuff with this in the next chapter. Okay, bye.